Okay, hello again, everybody. We are looking today at dimensional and unit analysis in physics, normally done at the CAPE or advanced level, as well as the A-level syllabus. And one of the things we have to note is that this is actually used to test for homogeneity or homogeneous equations, as we want to say, homogeneous equations, however you pronounce it, right? Now, the thing about it is that what we know so far is that a physical quantity can be measured by using some instrument in a laboratory setting. That is not the only thing that we need to know. What we do need to know to be able to break down these units and hence the dimensions, etc., these quantities, are what are the basic quantities. Of course, these basic quantities will also have basic units. Everything stems from this. I'm just going to put units, right? Please note the symbols I'm about to write. You may have learned it as five, quantities. At this level, it's considered to be 7. So the first basic quantity is mass, the symbol for which is m, unit is the kilogram. I'm just writing the symbol for now. I'm writing a symbol for your quantity because this is what makes up our dimension. Length is our another value, another quantity, capital L or common L, the unit for which is meter. Alright, so what we also have is time. Of course, unit for time, the symbol for time is common T, unit is a second. Then we have our electric current. So something you may or may not have met, it's fine. Capital I, the symbol is the ampere, capital A. We also have met, the unit for temperature. Of course, temperature being capital T. I'm just putting TEMP. The unit which is Kelvin, after Lord Kelvin himself. You will have also met the unit for luminosity, which is of course the candela. And lastly, we have the quantity called, of course, chemistry students, you'll know this one really well. The unit for which is called also the mole. These are all our basic quantities. Now keep in mind why we took a note of this is because these quantities make up our dimensions. These are the dimensions that we're actually going to look at, right? And of course, what we are also going to pay attention to is that these units, these basic units, what we are looking at right now, would make up all derived or other types of units. If it's not under this category, it makes up derived quantities and hence units. So why do we need to know this? Well, to first to be able to dimensionally assess or have any unit assessment or analysis of an equation and hence test for its homogeneity, we'll need to know these basic quantities. Alright, so we're going to just clear the sheet and begin. Okay, so to begin with, let's take a simple example of an equation and break it down in terms of its dimension. So we're going to analyze, do an analysis, as you say, in terms of an object's dimensions, and of course, in terms of units. So let's do both of them, right? So we have a better understanding of it. So let's take a simple example. Density equals mass over volume. Now density we know is rho. Symbol for density is called rho. Greek alphabet. You don't have to use it. It's fine. However, let's break down the dimensions. Mass, this is already part of what we need to know. Mass is a basic quantity. So in terms of dimensions, I'm just going to write dimensions like this. Mass is, the symbol is still m. Volume, however, is actually given by a basic formula called L cubed. This is the basic quantity that gives us volume, which is of course length. This is our dimension that we're looking at. This can also be written as ml to the power of minus 3. Now, that's all well and fine. Let's take the same unit, same definition, same quantity, of course, same equation, and break it down in terms of its units. Well, let's check it. Basic quantities, basic or SI units are what we're going to be looking at from the last slide. Now, what we also need to know is that mass is measured in kilograms, which we know is also a basic quantity. We get volume once again from length being cubed and a general formula, and length is measured in meters. So we get kilogram per meter cube, which is pretty straightforward, pretty familiar to us. Of course, this is written as this. Unit analysis, dimensional analysis. So dimensional analysis gives us an insight in terms of basic quantities that makes up that particular equation. Unit analysis gives us the SI or base units that make up the same equation. Okay, let's clear this page. Okay, so in an equation like this, how will we find let's use dimensions, or dimensions as you want to say it, right? Now let's check. Force is given by, and use the equation to help you. Force by definition is equal to mass by acceleration, a product of such two quantities. So I'm going to put ma over time as my left hand, so I'm breaking down the equation as we go along, what we already know. Momentum is known as common P. It's mass by velocity. So let's check. Mass by velocity over speed, symbol is the same. This will cancel right away. Now what we end up with is ma over t. And before we even go any further, is acceleration per unit time the same as velocity? No, but not even that. The velocity went off on a limb on the equation. So this is actually not the same. So we see based on the dimensions, this equation is not homogeneous. Let's get a new page and do the same equation for, well, of course, using the units. Okay, so one of our more classic examples is a comparison between energy and work. And of course, not even a comparison, it's actually the same. Work, we say, is normally energy, despite what type of energy we are looking at, right? Now let's take a simple type of energy that we're all familiar with and that has an equation. And we say, okay, let's look at kinetic energy. Kinetic energy by formula that helps us out is a half mv squared. Now I deliberately use this because I want to show you what happens to that half. That's a constant, which of course in this case has no units. So what we also have happening here, because it's a constant, please note we're actually not going to even bother to break this down. What we will get instead, we know energy in terms, let's look at the units. In this case, it's measured in joule. Kinetic energy, potential energy, whatever type of energy you're looking at is measured in joules. The unit for mass, of course, these are units, right? Let's check. What is joules? The joule is broken down to what? Basic quantity. Mass is measured in kilograms. Velocity is measured in meters per second, but please note the entire thing is being squared. So we square our units. A little bit of indices involved here. This is mass by itself, but to the power of 1. That is understood at least. So you get a joule, therefore, is equal to kilogram. Meters, everything outside the bracket should be squared. Power to a higher power is plenty power, as my teacher used to say. Meters squared per second squared. This is what a joule is. Now let's see if the same equation holds if we use our definition for work done. Work done is force by its parallel distance, so distance in the same direction in which an object is moving. And we also know, using the same concept of units, we should get the same thing. Let's see if we do. The joule is still used to measure work. Force is the Newton, measured in newtons, of course. Distance is measured in meters. Whether it's parallel or perpendicular, distance is distance. But how do we break down that Newton? From our equation for force, F is equal to ma, we get our units as kilogram meters per second squared. I'm just going to add that right here. So our joule, therefore, is going to be kilogram, put it in brackets, meters per second squared by the meter. Now, this again, indices. We have two bases that are the same, meters, and the power here is understood to be 1. For those of you who need to see it, we can do it like this. Kilogram, I'm going to bring my m's together. M to the power of 1, m to the power of 1, s to the power of minus 2. Multiply two numbers of the same base, what do we get? We add our powers. So we will get the kilogram meters, 1 plus 1 is 2, meters squared, hence we get meters squared, s to the power of minus 2. This is the equivalent of the joule. And of course, it still holds. They are equal to each other. Both equations we say are homogeneous. But let's take it up a notch. What do we use this for? Can we use this to find anything else but to just prove whether an equation is homogeneous or not? Well, let's find out. Okay, so here we have our first example where we are asked a few different things in a question like this. So we are given an equation where we have density being rho and pressure, of course, of a gas being P, related by an equation given below. Um, Now, they told us here that gamma is actually a constant. If gamma is a constant, well, that's a lot of help for us because we would need to include it as part of our analysis. All right, and we will use unit analysis for this one. So we will actually determine the base unit of rho. Of course, we know first of all that that is density. We want then asked to show that the base units of pressure is kilogram meter per meter, sorry, per second squared, and of course, and then asked to determine the unit for C. So let's begin one time. In our solution, the first thing we should note is that density is given by the equation mass over volume. And since density is mass over volume, and looking at the basic units, and of course this is one of the easier ones to look at, it's kilogram per meter cube as we just would have worked it out, right? Number two, show that the base units of pressure, well, of course, is this. Going to look at pressure from our formula. Pressure is equal to force over area. The unit of force is, of course, in Newton. Unit for area is meters squared. We can't go any further than a meter squared because that is a base unit. But we can now break down in Newton. Of course, we just did, so it's a kilogram meters per second squared all over meters squared. Once again, indices. And a rule applies. You divide in here numbers of the same base, you minus or subtract your power. So we get kilogram, 1 minus 2, of course. It is minus 1 s to the power of minus 2. And there we have our first proof. I'm going to clear the sheet and get the unit, of course, for C. Okay, so our last part of the question will really to find our units for C, and I just wrote the equation back. I'm going to now introduce, of course, using our formula for each of the equations that we have for both pressure and density, which is of course part 1 and part 2 of our question. We want to now obtain our units, but let's write based on our formula first. Pressure is actually force over area by definition, and density it's mass over volume. We can now break that down because what we are going to get, it's now the units for each of both of them, right? So what we're going to pay attention to here is that the unit we said for force over area, and of course we had it just now, we wrote it down before, it's kilogram per meter per second squared over our unit for volume, which we already knew, kilogram per meter cube. We can cancel our kilogram because of course, and if we are applying the indices, it still holds. So what we're going to get here is the rule. Of course, this is the rule where you're subtracting numbers of the same base if you're dividing them. The powers, that is. So we get meters, of course. This is of course minus 3, so you get meters squared. 1 minus 3 is meters squared per second squared. Now, this again is indices because the square root sign means that we can now express both powers to the power of a half. And if we express it to the power of a half, what it means is that both powers must be multiplied. 2 by a half, if you can't remember, it's 1. So we get meters per second. Meter per second. This is our unit for C. And please note, we will normally write speed as the speed of light in a vacuum. Alright, so we're going to do an example here where we are now given another question, but it's a little different what we'd have met. We know we can use a homogeneous equation to solve for unknown variables. So we are given an equation here where velocity is directly proportional to tension to some power x by mass to some power y, which of course we don't know, and L to some power z. These three letters, or variables as we call them, are unknowns, and we want to find out what those values are. So in this question, we're going to use dimensions, just to make sure we are okay with using both dimensions or units. So going back to what velocity is, by definition, velocity is displacement over time, but displacement is still a length, and that's a basic quantity over time. Symbols for both, we're going to use L over common T, and of course that is going to give me our left hand side. If it's dimensionally, so on the left-hand side, sorry, our left-hand side should be equal to our right-hand side. Well, let's see. So the velocity on the left-hand side, in terms of dimensions, will end up being length per unit time. On your right-hand side, I'm going to leave it as okay, I'm going to write it as a proportional sign as given to us, right? Our right-hand side, this is tension. Please remember, tension is still a force, and a force is given as mass by acceleration. Keep in mind, mass is our quantity. Acceleration is really velocity over time. See where we're getting at it? So, of course, at this point, we know velocity is length per unit time. So what do we get? Right, so just to continue now, what we have actually here taking place is the fact that if tension is a force and force is mass by acceleration, then our dimensions, and not our units, not to mix it up, will end up being, of course, length per unit time squared, because of course this will give us meters per second squared if we so break it down in terms of units, okay, not to mix it up. So on the right hand side, our tensional force is going to be, yes, we mentioned that it's mass by, of course this is acceleration, so it is mass by all of this, but please note it's mass by length per unit, sorry, time squared, but it's all raised to the power of x because our tensional force is raised to the power of x. So of course this is where it gets quite interesting. And of course in breaking down everything else, mass is still mass. I'm gonna put a dot so we'll know to the power of y. And length is still length, base also another basic quantity to the power of z. So this is really one we have to pay attention to. So once again we're going to use indices. So LT to the power of minus 1 is directly proportional to everything inside of here is raised to the power of x, which is that power outside. So we get m to the power of x, L to the power of x, t to the power of, keep in mind this is minus 2 by x, so it's minus 2x by m to the power of y, L to the power of z. Let's do some grouping, shall we? So I'm leaving my left-hand side as it is. Bringing my m's together, I will end up m to the power of x multiplied by m to the power of y. I'm going to put a bracket around it so you'll know that we already used it. If you think you're going to forget, you can cross them out. Not to say that they cancel off or anything like that, but it's just to note that they are actually being used. So, of course, bringing L together, L to the power of x multiplied by L to the power of z, brackets again, and we just have one t value, which is t to the power, I'm still putting in brackets, minus 2x. Now, that's all well and fine. It's directly proportional, we know that because we have a constant involved, right? But let's now do a little bit of, well, we can, at least from here now, is just maths. So let's bring some equations or some equating powers on both sides, alright? Using the law of indices. So I'm going to say, put a little step, so we will know. Equating indices or powers on both sides of our equation. You can see on the left hand side and right hand side. We will end up with, let's take the m term. I'm going to use the m term first. No, what about the m term? It's so interesting. So we have literally three terms. We have, I'm just going to break it down first. Our m term, our L term, and our t, which is time, 2. And of course, our m term, there's nothing here. M is to the power of 0. That will give us that value of 1. So I'm going to actually write the left-hand side as being 0 is equal to, what do we do with two powers of the same base? We add them. Multiplying, oh sorry, if we are multiplying two numbers of the same base, we add the powers, x plus y. That's our first equation. What happens to L? L here is to the power of 1. So what we will get is 1 is equal to x plus z. It's not as easy as canceling, and we know this. And of course, the time term, its left-hand side minus 1 is equal to minus 2x. And this is the first one that we can actually solve. So, right here, where our time term is listed, we can solve because there's only one variable. I'm writing it here. So if minus 1 is equal to minus 2x, if we cancel our minus signs, we will get 1 is equal to 2x. Mathematically speaking, x therefore is equal to a half. We got our first power. Here, should be easy, shouldn't it? I'm going to clear some space on my left-hand side where our equation is given. We'll use another page in a little bit too. So what we want to pay attention to very quickly is the fact that we will come back to revisit our equation and note why it's actually written with a proportional sign. But keep in mind that for now we are interested in finding our powers. We just found one power, we found our x term. So we need now to find our y and our z term. And it's not so bad because of course in any of the equations given, there's only one or two powers involved, not all three. So I'm going to take my x, I'm going to substitute my x value, which is equal to a half, into, let's say, our equation with z. So into 1 is equal to x plus z. You could have easily labeled the equation 1, 2, and 3, that's fine. But this is our second equation, of course, this is the one that concerns L. So what we will get at this point is 1 is equal to a half plus z. So z or z, some people say, is also equal to a half. And that's also fine. Lastly, we want to say, therefore, we want to now find y. So if 0 is equal to x plus y, then 0 is equal to a half plus y. And by making y the subject, we will get 0 minus a half, which of course is minus a half, our only negative power. What does that mean? Let's clear our page. Alright, so taking it up a notch, we have just found our three powers. Three powers, x is equal to a half, z is also equal to a half, and y is equal to minus a half. Now our equation was v is equal to t to the power of x, m to the power of y, L to the power of z. Let's write them in, shall we? So v therefore is equal to t to the power of a half, m to the power of minus a half, and L to the power of a half. Oh, come on, that doesn't look too nice. Let's simplify. This negative power could now become a denominator. So what we will get, t to the power of a half by L to the power of a half. I'm leaving the powers as they are so you can see them, but m to the positive power of a half. And here's the best thing about all of this. They're all raised to the power of a half. There's a lot of math in this question, you'll realize, right? TL, over m, all raised to the power of a half, can also be written as, I think I went and put them as equal signs and they were proportional signs. I'm leaving it as a proportional sign. So v therefore is directly proportional to the square root, one big square root sign, tension by the length over mass. This is our equation. We have just used our values that we found for x, y, and z to recreate a simpler form of our equation. And that is one of the examples that we are going to meet. Alright, anything you'll need explained again, please feel free to ask, leave a comment below, and I'll get back to you as soon as I can. Thank you.